Okay, so today we're going to look at Vesper shapes or Vesper theory for different molecules. Okay, so this is essentially once you have your Lewis structure, taking a look at the Lewis structure and identifying the shape that that molecule will take on based on two principles. Okay, the number of bonding electron pairs it has and the number of valence electron pairs it has. Okay. So there are a couple of assumptions that we have to take on, and some of you may know some shapes already. Actually, when we looked at hybridization, we've already talked about 3 different shapes. In grade 11, you may have talked about some of the simpler shapes as well, right? So for example, water, right? So water, I'm hoping at this point, right, you understand that water has this bent structure to it. So we're just going to go through all of the shapes. Some of them you're going to know already, and some of them will be brand new. But that's because you're now expanding your knowledge and the different types of molecules that we can discuss. So there are a couple of assumptions to keep in mind when we are looking at shapes and why these shapes exist. So first of all, we know electrons all have the same charge, right? So they all have negative charges. And we know that like charges repel. So what does that mean? We know electrons are all negatively charged and they want to be as far apart as they possibly can. So the shapes that these molecules occupy really will, the angle of the bonds are going to change because it depends on the number of electrons that are kind of hovering around the central atom. And we'll look into that. So electron pairs and molecules will be situated as far apart as possible, which is what we already mentioned. Valence electrons occupy regions of space so that shared pairs of electrons are evenly spread out around the central atom. Okay, so essentially, these electrons, right, anytime we're talking about bonding electrons, we're always talking about valence, right? So that means the highest n number and the s and p electrons within that n number. Okay, so when we're looking at oxygen in the bonds that they're making, right, the bonds and the electrons that are involved here are only the valence. So meaning, yes, they do have other orbitals, of course, but they are internal orbitals. So meaning the energy levels are lower and they're completely full, right? So in order to make a bond, you need a half-filled orbital. And of course, if you have a lone pair of electrons, that's really a full orbital, right? So these 2 electrons, they're not being shared with anybody. They're in their own orbital themselves around the oxygen atom. Okay, and of course we know that the spaces are going to spread out evenly for all of the reasons we just mentioned above. All right, so now we're just going to get into a bunch of shapes. So it's going to be very repetitive. Obviously the shapes are different. Sometimes they go by different names as well, so I will mention that as we go. So first of all, before we even get into anything, I want to explain some of the kind of general formulas you're going to see. So A represents the central atom, okay? So when you say AX2, that means that there is one central atom. X represents a peripheral atom. So what that means is it's representing something that is bonded to the central atom. So in this case, when we see AX2, we have a central atom with 2 other elements or other atoms that are bonded to it. You're also going to come across the letter E. The letter E represents a lone pair of electrons. Okay, so for example, if you see AX2E2, that means that you have a central atom with 2 atoms bonded to it, and they could be the same element or different elements. It doesn't matter, it's just atoms in general. And then it has 2 lone pairs of electrons. Remember, this is always in reference to what is happening at the central atom. Okay, so now that that's kind of out of the way, let's look at our first shape. So linear. So linear, of course, means when you're looking at the shape, it appears as if it's a straight line, right? So it's 180 degrees between the 2 bonding elements. So here we have 2 single covalent bonds. Now, actually, I'm going to talk about that a little bit later on, but let's continue from here. So you have 180 degrees. There are no lone pairs. So notice here we have a central atom, and we have 2 other bonding elements. In this case, our example is beryllium with 2 hydrogens. There are no lone pairs around that central atom. So obviously, The furthest apart that they can possibly be from one another are going to be 180 degrees. Okay, now when you're discussing Vesper shapes or molecular shapes, actually, I know this mentions 2 single bonds, but to be honest, single, double, or triple bonds are actually not even considered here. You're literally just looking at the number of of atoms. So for example, let's look at carbon dioxide. Carbon, double bond oxygen, and then another double bond oxygen. Okay, so let's look at the structure. So you have carbon, which is the central atom. It has 2 other atoms bonded to it, and it does not have any lone pairs. So this would also classify as being linear, right? You have the oxygens directly opposite of one another. So even though it's not 2 single covalent bonds, we have 2 double bonds, that doesn't really matter. So it mentions this because that's the most common, I guess, outcome. But really what you're looking for is this. You have a central atom with 2 bonding elements with no lone pairs around the carbon. Okay, so next we have trigonal planar. So trigonal planar, look at the general formula. We have 1 central atom with 3 other elements bonded to that central atom with no lone pairs. So again, no lone pairs. So there are 3 things in total. So the angles, right, are 120 degrees between each one. So notice there's no lone pair. So the example we're using here is boron. This is actually boron trihydride. Sometimes you'll see it generalized as just hydride because it's assumed boron's making 3, but the proper terminology is trihydride there. Okay, yeah, so let's go to the next one. Okay, so tetrahedral. So tetrahedral, again, look at the general formula. This is where you have 1 central atom with 4 elements bonded to that central atom, or 4 peripheral atoms. So a classic example here is methane. So you have a carbon. It has 4 hydrogens. There are no lone pairs around that carbon. So when you have 4 in a 3D structure, you can always imagine it in front of you, and we'll look at a simulator after. Each angle is 109.5 degrees. Okay, so now we're going to have angles that are going to pop up for every shape. The only 3 shapes I expect you to know are these first 3. Okay, so linear, right, trigonal planar, and tetrahedral. Okay, so those first 3. So basically 180, right? So let's go back, right? Just to recap, 180, right? 120, and 109.5. Okay, so all other angles you are not expected to know at this grade 12 level. Okay, obviously if you continue on in later years in chemistry, you may have to, obviously especially if you're going into atomic theory or theoretical chemistry, right, you're gonna obviously go delve deep, even deeper than what we're gonna be looking at here, like way deeper, like way deep. But for now, right, these are the angles I expect you to know. You do need to know every shape that we are discussing. So when you're drawing a Lewis structure, you should now be able to predict the shape after going through this lesson. So trust me, that's enough to know. Okay, so you have 3 different angles that I'd like you to know. Okay, so we're going to continue on with the shapes. So remember, from here on out, you're going to see the angles. Don't worry about the angles right here. Okay, so we have trigonal pyramidal. So trigonal pyramidal is where you have, now it's our first instance looking at lone pairs of electrons, C to E. So in here we have a central atom, 3 peripheral atoms, 3 elements bonded to the central, and 1 lone pair of electrons. So I want you to notice something. So ammonia is our classic example, just to compare. Okay, so lone pairs of electrons actually occupy more space than bonding electrons do. Okay, so for example, our boron here, and I know you don't need to know this bond angle, but I'm just going to use this as a comparison, okay? So the bond angle when you have 3 atoms and no lone pairs are all equivalent around, which is 120, right? 120, 120, 120. As soon as you introduce a lone pair of electrons, notice the bond angle of those three elements becomes smaller. Okay, it's almost like they're being squeezed together in comparison to when you have three on this side. So what happens here is because this lone pair, you have to imagine, right, these are in their own orbital. The orbital is a volume of space, right, where the electrons are essentially within, and you have to remember those electrons are repelling each other, right? So the lone pairs of electrons around central atoms will occupy more space than when you have just bonding electrons. So you're going to notice that when you add in lone pairs, right, it's obviously going to shift around where those peripheral atoms are located. So just something to keep in mind when you're looking at it, right? So that's trigonal pyramidal. So angular or bent also goes by another name, V-shape or V-shaped. So any of these are acceptable when we're discussing this type of shape. Okay, so let's look at the formula. So here you have a central atom, two bonding elements, and you have two lone pairs of electrons. So here's our lovely water, right? So water, oxygen has two bonding atoms and two lone pairs of electrons. So again, these electrons, these lone pairs, are occupying more space than those hydrogen bonds are occupying. So it's almost like those hydrogens are kind of being pushed together because the electrons that are on that oxygen, they are repelling each other down. Okay, and actually it's mentioned here again. All right, so angular, bent, V-shape, those are all good. Either, you just have to give me one, right? So for cycle, H2O, what's the molecular shape? What's the Vesper shape? Any one of those. Okay, next, so we have here trigonal bipyramidal. So we're getting a little bit more complex. And actually, if you take a look at what's going on here, right, we're violating the octet rule. So some of the ones earlier on, like our boron trihydride, also violated the octet rule, but we're used to seeing those from the Lewis structures. So now we're looking at more complex shapes. So trigonal bipyramidal is where you have a central atom, 5 bonding elements, and you have no lone pairs of electrons here, okay? So when you're drawing these, right, you have to keep in mind, well, the Lewis structure you draw, this is actually why you do Lewis structure in grade 11 and you do it again in grade 12, because if you have the incorrect Lewis structure, that's going to impact what shape you dictate that it is. Okay, so it's really important that you practice your Lewis structure drawings. Okay, so octahedral. So octahedral is where you have a central atom with 6 elements that are bonded to it with, again, no lone pairs of electrons. So sulfur hexafluoride is an example of one here. So you have sulfur with the 6 fluorines. So again, don't worry about the angles for anything other than those first 3 I'd like you to know. So what we're looking at here, this idea of electron pairs distributing themselves around the central atom to occupy, to repel and get as much space as possible. So this theory, you've heard me say Vesper a lot, right? Okay, so Vesper is actually an acronym for this theory that we're using to explain shapes of molecules. So it's valence, shell, electron, pair, repulsion. So electrons in the valence shell will repel, essentially. So it goes back to all those assumptions that we made at the very beginning. Okay, so we're going to recap. There are more shapes that I'd like you to know. So that's this first little block are kind of like the general shapes. Okay, there are more shapes because, of course, we have more variations of lone pairs and bonding elements that we can have. So we'll look at that in the next part.